Welcome back, everyone, to part 3 of chapter 9. We're going to be departing from the topic of center of mass to discuss momentum. And momentum, by definition, is the combination of mass and velocity for an object. Now, this is not really something new because we've already seen a combination of mass and velocity in a previous expression in terms of kinetic energy. But now we want to basically mirror what we've seen from Newton's second law, which takes mass times acceleration and relates that to force. And so we're going to take mass times velocity now, and we'll give that the title of momentum. Now, since we're already using M for mass, we need a different letter to stand in for momentum, something else in the alphabet that's not currently in use, and that is going to be the letter P. Now, the big difference between momentum and kinetic energy, aside from the fact that we're missing the squared term and the 1/2, is that momentum is going to retain the vector information about the velocity, whereas kinetic energy only uses the magnitude of the velocity or the speed. So the kinetic energy doesn't have any information about what direction our mass is moving, but momentum does. Because of that, we have to go back and start using all the knowledge that we've been using about vectors, vector addition, vector components, etc. We've had it kind of easy the last 2 chapters with chapter 7, chapter 8, because even though we were still using vectors, we were converting them into scalar quantities, hence energy. And it made dealing with a lot of the physics easier because we didn't have to keep track of all of those vector directions and components. But now we do. So we have to go back and refresh ourselves on how we're going to combine these vector components, break them up, put them back together, etc. And eventually we're going to come to a point where we want to conserve the momentum in a system. And we're going to add an extra word into this. We're going to call this linear momentum. And that's because momentum has a direction aspect that is associated with it. So if we want to think of a mass that is moving with a given velocity, well, that velocity vector, it's pointing in a given direction or in a line. By combining the mass and the velocity together, we have a vector that we call momentum, and that equality statement says that we have to have the same thing on both sides of the expression. Not only do we have to have the same numerical value on both sides, but now we have to have equal directions associated with the vectors. So whatever direction our velocity is pointing, that's the direction of the momentum, and vice versa. The units that we're going to associate with momentum, we have units of kilograms for the mass, and we have units of meters per second for the velocity. Now, that looks very close to being a Newton, but keep in mind that a Newton is a kilogram meter per second squared. So we're actually missing the second squared in the denominator, but we can make up for that just by multiplying and dividing by a second. And so now we have units that we call a Newton second. And playing around with the units is a very powerful way of coming up with other ways of expressing the physics that's going on. Because now I have units of force and units of time that are equaling the same thing that we have for mass and velocity. So does this mean that force times time is equal to momentum as well? In terms of the units, yes, but this is not going to be a direct equality. When we think about a force, what does a force do to a velocity? Newton's second law says force equals ma. Acceleration is a change in velocity with respect to time. And if force can be related to momentum, I'm going to replace force with momentum over time. Well, acceleration was defined as the change in velocity over time, so that means that we would actually have to call this a change in momentum. But that should make perfect sense now, because if I have a change in velocity on one side of the expression, and if mass times velocity is now our definition of momentum, what we do to one side of the expression we have to do to the other, and that includes any delta statements. And we already know back from the very first chapter of this semester that we can have a mass that changes its velocity. As such, that means that our mass can change its momentum. That's going to have to happen as the result of some force that acts on our mass. And I'm getting this expression from the unit shuffling that we did right above there. The one thing that we do need to be careful of, however, is that delta t value. Is delta t large? Is it small? At this point, we really don't know. To make things easier on us, I just say that delta t is too big, and so that means the best that we can hope for out of this statement is an average force. If we expect to get an instantaneous force value, then we will need to have some function for the momentum that describes how it changes with respect to time. From there, we can apply the calculus, we can take a derivative, and we can get an instantaneous value for the force at any given time. Okay, so how is all of this helpful to us? Well, now that we can see a change in momentum, we can relate that change in momentum to a force that acts over a certain amount of time. And the example problem that I like to give for this is a child that climbs a tree. So we'll go ahead and put that example problem together. I'll see if I can draw a tree here. So we have a tree. We'll put some leaves on the tree. And there's a branch on the tree. There's a child that climbs out onto the branch. Sitting on the branch there. We'll say the branch is about 5 meters from the ground. And then it's lunchtime. So child has to get out of the tree. And instead of climbing down the tree, well, it's just easier if we just jump out of the tree, right? Well, keep in mind that this child doesn't know anything about physics. They haven't taken a physics class yet. And so they jump out of this tree, and in landing at the ground, the child has to somehow take the impact velocity of falling out of the tree or jumping out of the tree, and we have to turn that impact velocity into a final velocity of 0. That's not something that we've really done yet in any of our problems. We've been focused a lot on starting with some initial velocity and figuring out what the impact velocity is going to be when we get to the ground. But then, after that impact, well, how long does it take for us to change our velocity again until we can reach that final velocity of 0? That time interval is going to clue us in as to how much of a force we are going to experience during this change of velocity. But we also have the mass of the child to consider. Any change in the velocity paired with the mass will result in a change in momentum. And if there is a time interval associated with that, well, both sides of this equation are now going to relate to a force. Now, if that time interval is very small, that's going to result in a very large force. And this child, being that they haven't taken a physics class before, their first mistake, obviously, is jumping out of a tree from a height of 5 meters, which is a little bit more than 15 feet. But they're going to lock their knees when they land. And I can already hear some of you going, ooh, because in locking the knees, it's going to make for a very, very, very short time interval. In fact, we'll say that this is 100 milliseconds. Let's back that off. We'll say 10 milliseconds. Okay, so I would like to know what is the average force that this child experiences during the landing. We'll give the child a mass of, let's say, 30 kilograms. We know the child is starting from a height of 5 meters. They'll jump down to the ground. But if I'm going to know how the momentum changes during the impact, I'm going to have to know how the velocity changes at the impact. To help us out with that, we will start at the beginning, where the child has 0 initial velocity, and we'll let them jump down to the ground. And we will use conservation of energy to tell us what the velocity at the impact site should be. Now we'll assume that the child starts from rest at the branch, and so the initial kinetic energy will be 0. The initial potential energy will be based on how high above the 0 point we are, and we'll just go ahead and let ground level be the 0 point for our potential energy. So our initial potential energy becomes the mass of the child times g times h, which we know is 5 meters. That will have to equal the final kinetic energy at the impact site plus the final potential energy at the impact site. But the impact site is down at the ground where the potential energy is 0. In this case, the mass of the child is not required because anybody that jumps out of the tree should fall under the same influence of gravity, and they should all impact the ground with the same velocity, vi, which, let's see, initial velocity was 0. We can drop that term out. Impact velocity is going to be root of 2gh. So in the case of the child jumping out of the tree at an initial height of 5 meters, we'll plug all of this in to our calculator. 2, 9.8, and 5. Square root of that is just a little bit shy of 10 meters per second. I'm getting 9.9. So that's the velocity at impact. We now have to use that in our change in momentum expression to find out what the average amount of force is going to be. And that average amount of force is going to come from the change in momentum with respect to time. That's exactly what we have written over here, only we're going to use the change in velocity times the mass. All right, here we go. Mass of the child is 30 kilograms. The change in velocity. This change in velocity, delta V, is during the impact. And so the initial velocity of this impact is the impact velocity. The final velocity of the impact is when we achieve 0 velocity after colliding with the ground. So we have 0 minus the impact velocity, 9.9. So we have a negative 9.9 for the change in velocity. Negative 9.9. All divided by the time interval of, what did we say, 10 milliseconds? So that's going to be 10 times 10 to the minus 3. Get my calculator app open again. 30 times 9.9 divided by 10 times 10 to the negative 3 makes 4. An average force that is equal to 29,700 newtons. Now there is that negative sign there. We do need to talk about what that means and where that came from. You'll notice in my picture, I did not specify a reference frame. And anytime we're working with vectors, we do need to have a reference frame. Since the child is falling, and we're going to see all of the motion of the problem pointing down, I'm going to go ahead and let down be the positive direction for this system. So that means that when we impact the ground, our impact velocity is down in the positive direction. That is a positive 9.9 meters per second. Well, that's what I got out of the math here, but Using conservation of energy, really the only thing we get is speed. We don't get direction. But now I have a direction associated with this problem. The more important part is right here. What happens when we impact? How does that velocity change? Well, I went from a positive velocity to a zero velocity. That's a change that is negative. I had to slow down. The only way that that could happen is if the child encountered a force from the ground that pushed in an opposite direction from what they were traveling. The child jumped out of the tree, their velocity was oriented down, but then we had to go from 9.9 meters per second to zero. The only way to slow the child down would be to have a force operating in the other direction. Well, that other direction is the negative direction with respect to this reference frame. So that's where the negative sign comes from. That's why we have a negative 29,700 newtons. But let's talk about that amount of force. This child is experiencing a magnitude of 29,700 newtons for a period of 10 milliseconds. Now, that's not a whole lot of time, granted. But let's compare this force to the weight that the child typically experiences. The weight of the child is mg, so we have 39.8, and if we divide that by 30, oops, gotta reopen my All right, so this is coming out to be approximately 101 times greater. So when this child jumps down to the ground and they lock their knees for that 10 milliseconds, the child experiences a force that is just over 100 times greater than what they experience for their weight. So if you can imagine having 100 of you standing on your shoulder just for 10 milliseconds, well, do you think that that would do some damage to you? More than likely, it would probably compress your spine. It might cause your locked knees to unlock in the wrong direction. It could end up causing your knees to fold, quite possibly breaking the joint at the knee. That can cause a lot of damage. And granted, 5 meters is quite a jump out of a tree, but even jumping a meter and landing wrong can cause some pretty serious damage to the human body. So this child ends up in the hospital for obvious reasons. Two broken legs, we'll say. And as they're sitting there in the hospital recuperating, somebody brings them a physics book, and they learn about this idea of a change in momentum and average force. And this change in momentum, this delta P term that we had here, which is really just mass times change in velocity, this is called impulse. And it actually has a name and its own designation of capital J. Now, I really don't see the need in taking something that's already well established as delta P and having to give it its own name and a completely different letter to designate it. But this does show up in the book, and so you'll see the word impulse. You'll see the letter J as a vector. So we need to be aware of what that means and prepared to deal with it. I would just say, take that for what it's worth and rewrite it as delta P, and then you can rewrite delta P as M delta V, and all will be good. Okay, so this child reads up on an entire semester of physics and gets to this chapter on impulse, and they say, oh, now I understand. Now I see what went wrong. I locked my knees, and the time interval was too short. It is that time interval that caused such a drastic change in the momentum. Now, there's nothing that we can do about the change in the velocity. We're going to jump out of the tree. We're going to hit the ground at 9.9 meters per second, and we eventually have to come to a stop. There's absolutely nothing that we can do about that. But maybe we can do something about that time interval. Maybe we could extend that time interval. If we could make that time interval larger, it would reduce the average force that is experienced during that time interval. So this kid goes back to the tree after recovering, and they decide, all right, we're going to try this again. We're going to jump out of the tree. And when we jump out of the tree, we get the same impact velocity of 9.9 meters per second. We have the same change in velocity. We have to go from 9.9 to 0. So that's a negative 9.9 meters per second for a change in velocity. But now, instead of locking our knees, we're going to fold our knees. And we're not gonna stop there. As we fold our knees, we're also going to kind of let our body just go limp and sort of roll and collapse onto the ground. And what this is going to do is it's going to extend the amount of time that it takes for our body to come to a halt. But in rolling to our side, it's also going to allow a greater surface area of our body to absorb that force. Now, I don't recommend trying this on your own because it's not going to work out well. It's still going to hurt. But maybe by locking our knees and rolling, we're able to increase the time interval to an entire second. So we drop down, we bend our knees, we roll, and it takes us a full second to come to a halt. So how is that going to affect the overall average force that this child experiences? Let's put the numbers in and see. Mass, delta V, delta T. Mass of the child, we'll assume, is the same, 30. Change in velocity is the same, negative 9.9. But now the time interval has increased by 2 orders of magnitude. And that means that our average force is going to reduce by 2 orders of magnitude from what it was. Because we now just have the 1 second. This means that the average force that the child experiences during the landing has now dropped down to only about 300 newtons. And compared to the weight of the child, well, that's only about, let's see here. We have that right. I want to make sure I did this properly. We've got My phone just timed out. I gotta open it up again. Let's double check our numbers here real quick. Okay, so that is correct. And so now, if we looks like we're getting something just a tiny bit above the average amount of force that would be experienced. Looks like we get about 1.01 times the amount of force that would be experienced just standing there. So compared to the regular weight, the landing has the feeling of experiencing the weight. And so this is by far the safer alternative. Basically, we're just adding this amount to the normal weight that we're already experiencing, and so you'd feel about twice as heavy as what you normally would in this scenario. And feeling twice as heavy for about a second, it's going to be uncomfortable. It might, it might produce a little bit of pain in your knee or in your back for a little while, but it's something that you can deal with. It's probably not going to cause you irreparable damage to your body. It's probably not going to cause you to have to go to the hospital or spend months and months of rehab time. But just that simple act of allowing your body to go limp and rolling and extending that time interval has taken us from something of having to experience 100 times our own weight to just twice our own weight. And that could be the difference between life and death. And this idea, this concept is utilized every day in the automotive industry, because you have people that are in car accidents where the body of the person is initially traveling at the same speed as what the vehicle is. But then if the vehicle collides with something, the velocity of the vehicle and the person inside have to achieve a zero velocity within a fairly short time interval. So if you can imagine, you're driving down the road one day at 60 miles an hour, you hit a patch of ice, you lose control, and you end up slamming into a light pole or something similar. So you have to go from that 60 miles an hour to zero in a really short time interval, like maybe it could end up being something like 10 milliseconds. And 60 miles an hour, if we convert that to meters per second, let's see if I can do this. There's 1.6 kilometers for every mile. So miles per hour, 1.6 kilometers per mile. Thousand meters per kilometer. And then we have 3,600 seconds per hour. So we'll go ahead and make that conversion here. 60 miles an hour. That works out to be approximately 26.7 meters per second. Right. So we have to go from 26.7 meters per second to 0 over a time interval of the 10 milliseconds, which is 0.01 seconds. That actually sounds kind of short, but we'll go with it. And then obviously the average force that you experience is going to depend on the mass of the passenger. But mass of passenger aside, let's just see what we get here. There's 27. We got 2 decimal points here that we're going to have to move over. There's that minus sign there, and that's because the average force that we experience during the collision will have to push us back in the opposite direction. But let's take a person of 100 kilograms. They're going to experience approximately 267,000 newtons worth of force, which would be approximately 270 times their weight. So if you can imagine 270 times your own weight pressing down on you, even for a very, very short time, it's probably going to cause quite a bit of damage, broken bones, internal bleeding, etc. And so how do we save lives? How do we get these people to walk away from the crash as opposed to being carried away? And again, there's nothing that we can do about the change in the velocity. We still have to go from 26.7 meters per second to 0 meters per second. There's nothing that we can do about the mass of you. But what we could do is we could extend the amount of time that it takes for the passenger to come to a halt. And this is done in a multiple avenues. One way is to have an airbag system. And so when the airbag deploys, it allows for the person to have the majority of their momentum absorbed by the pillow of the airbag, and it extends the time interval. And as that time interval increases, the average force that the person experiences decreases. Now, that's not to say that it's not going to hurt. Airbag deployment is very fast, and your body is still going to be brought to a halt over a very quick time interval, but it's a time interval that's long enough to reduce the average force so that it doesn't cause as much damage to you. Now, you still might end up with scrapes, bloody nose, laceration, maybe even some broken bones as a result. But that's far better than having your body slam into the dashboard or the steering wheel, in which case most of the bones in your chest are probably going to end up being broken, and you probably would not survive. The other way that we can extend the time interval during the crash is that a lot of vehicles today are designed with what are called crumple zones. And these are zones where the car will literally crumple, and in doing so, it is the car that absorbs the majority of the change in momentum of the system so that you don't have to. Now, there are a lot of people that I see that get very upset when they get into a fender bender because these crumple zones basically make the vehicle inoperable. It basically totals the car, and they have to get into their car, and now they're upset that they have to spend money. They have to go through the process of talking with the insurance company, but they completely forget about the fact that they're still alive. And it's the combination of that crumple zone. You're going to have these crumple zones on the front and the back of the vehicle. You have the airbags. A lot of vehicles now don't just have the driver airbag; they have the passenger airbag. Some of them will even have side airbags on door windows. And when these airbags go off, they're going off to protect you and to save your life. But if you've ever had an airbag that's been deployed in a vehicle and you're still driving that vehicle, you want to make sure that that airbag has been reset, because they're only good for one time, and then you have to replace them. And unfortunately, they're kind of expensive. My dad has had an airbag go off in his truck, and it cost him about $500 to get it reset. But that is definitely something that is worth doing, because those airbags can save your life if you're ever in a serious accident like this. So that is momentum, and this is how momentum relates to average force along with the time interval. And so we've seen the importance of increasing that time interval so that we can decrease the amount of average force that is encountered. But we've also seen how, given that momentum is a vector, we have to start treating it as a vector with the appropriate reference frame. And when we come back for the fourth video, we're going to look at some situations that involve more types of collisions. Both of the examples that we've seen here, both with the child jumping out of the tree and the car crash, can be categorized into what we call collisions. In the case of the child collided with the ground. Doesn't quite seem like what we would consider a collision, but that is in fact what happened. And so we need to see what happens during collisions in terms of the momentum, but also in terms of the energy. Because these equations for energy are not going to be as useful to us during collisions as they were when we were just moving from one spot to another. So until then, we'll see you at part 4.